Okay, so now what we're going to do is we're going to build this on Simulink. We're going to build all three of the models that we have here. That is these three models. We're going to build them and we're going to run those outputs to see if we can get that. So as you can see, we'll need three transfer functions. So the first thing that we need to do is to have three transfer function blocks. Okay, so we have one. And once you have the one, all you need to do is you can actually copy and paste two more, which is easier, or you can do the same trick, that is to type in transfer function on the three of them. So on the first one, let's open it up. Let's have a look at what are the roots that we have. It is going to be 1, 4 and 24.52, right? So it's going to be 24.52 as the numerator. So we go over here and we put 24.52. Then at the denominator we have 1, we have 4 and 24.52, right? We apply and we click OK, and if you just drag this open up a bit, you'll see that you have the first transfer function there, right? So now let's go into the second transfer function. And the second transfer function, if you multiply it in, that is the denominator, if you multiply it in, the numerator is going to be 245.42. So you can put the numerator as 245.42. And then on the denominator, what I did was that I used MATLAB and I multiplied the coefficients in using the con function. So the coefficients are s cubed plus 14s squared plus 64.52s plus 245.2. So this is something you can do on your calculator as well. So the coefficients are 1, 14, 64.52 and 245.20. So it's going to be 1, 14, 64.52 and 245.20. Then you click on that and then you apply. Let's see what we get. Yep, there we go. That's the second one that we have there. Now we go on to the third one, and we're going to do exactly the same thing, right? If you look at the MATLAB block that I have here, I put the blocks in convolution of 1, 3. Let's just check if they're correct. Yeah, 1, 3, 1, 4, 24.52. So they look correct. So it's going to be, the numerator in this case is slightly different. It's 73.626. So the numerator is 73.626, and then on the denominator you have 1, and I'm following this block here, 7, 36.52 and 73.56. Oops, 73.56. Apply, click OK. So we have the three blocks. Let's expand this one out as well. So we have the three blocks. Next I'm going to draw a scope output, and in the scope output I'm going to give 3 inputs. The reason is I want to couple them together. So the first output is going to go there, the second input is going to go to the second transfer function, and the third one is going to go into the third one. And let's say that we are using a step input as our source. The step input can have a step time of 1, does not matter. We're going to make the first connection, then we're going to make a second connection, and then we're going to make a third connection, right? So you can just make that over here so that they are in the same line. And once we are done there, we can just put this here. Yeah, right. Once we are done that, we're going to compile and run this block to see what is their response. As you can see, it's basically compiling. And once it's done compiling, let's look at the second order scope results. So you double click on the scope and we wait for the scope output that this has generated. Now our assumption is that if we go back to our study, we said that T1 and T2 by our calculations should be second order systems. That's what we calculated. And T3 should be slightly different. So here, this is the scope output. And you can see that the yellow and the blue lines represent T1 and T2, while the red line represents T3, right? And you can see that there's a close resemblance between T1 and T2, where T1 is a pure second order system. That's what we learned here, isn't it? If you have a look here, if you see the values, you see that T1 is a pure second order system, while T2, it was a third order system to start with, but we could equate that with the rule. We could say that it is a second order approximation which is valid, while T3 we calculated and found that a second order approximation is not valid. And this is validated by the figure that we have here on the scope output. So this is how you build that scope output and you test if a second order approximation is indeed valid. Now this is very useful when we go in to do our problems, because if you have a third order system or a question that requires you to answer questions, you first need to ensure that a second order approximation is valid, without which we will not be able to continue our work. Right. So this is that portion in your textbook which deals with second order approximations. So you can try this examples here on both MATLAB and Simulink. They are explained in Appendix B as well as in Appendix C. You can actually try this out. Now you can try skill assessment 4.6. Again, if you want to, you can try this on Simulink. The answers are given here. You can actually try it and see if it is indeed true using Simulink. They have also given you the MATLAB code to give a try here. All right. Now what would happen if you have a system with zeros? So all the systems that we look here, like for this example, it has no zeros. That means there is nothing on the numerator which is related to S. But what is the impact of adding zeros onto your circuit? That's what we're going to have a look at next. And here again, you can see this by a simple example here, right? So there are 4 cases that they are considering. Firstly, there is one without a zero, which is this line over here. Let's just zoom this in a bit so that we can have a very clear look at this. Right, so here you can see that the first one here, it is having no zeros, and the second one is having a 0 at -10, and then you have 0 at -5 and a 0 at -3. So the conclusion that you draw here is that the closer the 0 is to the origin, that is to the 0, 0 point, the higher overshoot that you have. You can see that the main difference here is in the overshoot as well as in the peak time. You can see that if you have a 0 very close to the origin, that is this one at -3, you have a very high overshoot. When you distance it a bit and it goes to -5, you'll see that the overshoot dips a bit. The further you go at -10, the overshoot again goes to a lower level. While if you have no 0, then your overshoot remains kind of the lowest from all three of this, right? You can see that although it has some variations here, they all have a settling time which is very close by. So the major factor that an additional 0 has, or impact it has, is on the overshoot. So if there's a specific application where overshoot is the main point of view, then adjusting the zeros in your circuit will be able to get you that required percentage overshoot. But we will be discussing when it comes to the last chapters that is not always a straightforward method. We will need to do something called a pole zero cancellation if it comes to that point. But for the time being, what we need to understand is that having a 0 on the numerator, which will be on the numerator, and if it is close to the origin or to the 0 axis, then it creates a higher percentage overshoot. Whereas the further it goes away from the origin, the lower the second order, the percentage overshoot becomes. So this is another example. So we looked at what happens if a system has additional poles, as well as what happens if a system has additional zeros. So that now brings us to the end of the third module, or sorry, the second module. That was chapter 4 in your textbook. Now in your labs, along with the group work that we're doing, we'll be now doing the reduction of multiple subsystems. And in our theory class, we'll be going on to chapter 6, where we will be looking at the concept of stability. All right. Okay. Thank you.